All right, thank you so much. I'm really excited to be here, and thank you to the organizers for inviting me. I'll start by saying, in case you didn't read my abstract, that the content of this talk is not strictly within the realm of additive combinatorics, but the methods that I'll talk about do have some relation to additive combinatorics results, so I'll try to sort of highlight those. But the sort of main things that we'll be proving are really within the realm of more extremal or probabilistic combinatorics. But I did run this by the organizers beforehand, so I'm not just going like rogue when we start. But so I'll make sure, since some of you might not be familiar with the sort of the foundational problems in this area, to start from scratch. But yeah, please feel free to unmute yourself, ask any questions at all. I want to make sure that we are all on the same page before we get too far into the talk. So today I'm talking about a topological Teran problem. So let me just start by saying what the Teran problem is. And it's a pretty foundational question within extremal combinatorics. And it's the following. Given a graph H, how many edges can an n-vertex graph have while containing no isomorphic copy of H? So one of the sort of first, historical results was just looking at, for instance, H is equal to a triangle, right? And we have Mantel's theorem, which says that the max number of edges in a triangle-free graph. We actually know the answer to this. This is n squared over 4, and it's tight. In fact, this is achieved by the complete bipartite graph on parts of size n over 2. Right, that's the sort of densest triangle-free graph that you can possibly have. So, to explore this problem more, you want to look at different types of graphs H that we're forbidding in our n-vertex graph, and figuring out what these so-called extremal numbers are for those particular graphs. And the question was pretty much answered by Erdős for all graphs H except for one very important class of graphs, and that is the class of bipartite graphs. And that was what was the degenerate case in the result that Erdős proved. And so we often refer to that case as the degenerate degenerate Teran problem. So that's H bipartite. And a lot of work has been done on this question, but it still remains, in general, an open problem to figure out what the extremal number is for just bipartite graphs. So to keep this problem sort of interesting, we want to see what are other variants of this question we can ask. And there's one pretty natural generalization to make, and that is by just replacing graph with our uniform hypergraph. Where, our uniform hypergraph, now we're looking at a set of vertices and a collection of edges, which are subsets of size R. And I'll refer to that as an R graph. And we can ask the same question: how many edges of size R can an n-vertex hypergraph have while containing no isomorphic copy of your favorite R uniform hypergraph? And again, a lot has been done on this problem. And again, the sort of interesting case is the degenerate one, where you're looking at an R-partite R uniform graph. And so I want to take this question sort of one step further and give you a second variant, which is this. What if we replace the word isomorphic with the word homeomorphic? Now, this might seem a little bit less of a natural thing to ask, mainly because I haven't told you what it means for hypergraphs to be homeomorphic to each other. If you think back to when you last thought about topology, right, a homeomorphism, it intuitively tells us when two topological spaces are the same in a certain sense. And, technically it's a continuous map with a continuous inverse, but a priori, we don't have any topologies hanging out here. We're just dealing with these discrete structures of hypergraphs. So in order to tell you what exactly I mean when I ask this question, I'm going to take a pause and introduce the topological point of view that we'll be taking for this problem. And the topology I'll be using is that of a simplicial complex. So if you're not familiar with simplicial complexes, you can take these to be definitions. If you are, then we're not thinking about continuous simplicial complexes the way maybe topologists would prefer to think about them, but we're really thinking about the discrete or the combinatorial version of a simplicial complex, which is really just a set of vertices and a collection of subsets of those vertices. And we're not really embedding them in any sort of space. So I'm defining a simplicial complex as just a set of vertices and a family of subsets that's downclosed, right? So any element I have in my simplicial complex, all of its subsets are also in my simplicial complex. I'll call the elements simplices or faces, and I'll call the maximal faces facets. The dimension of a face, I'll just define to be the number of elements in it minus 1. And the dimension of my simplicial complex is going to be the maximum dimension of its faces. So if you haven't seen this before, this is a lot of new terminology, so I think it's best to illustrate with an example. So let's say I have a simplicial complex that looks like this, and I'll keep it within 2 dimensions so that I'm able to draw it. Let's say these are my vertices, and maybe I have an edge here. And I'll also shade this in to denote that this triple of vertices is in my simplicial complex. So my vertices, of course, are what I drew, A, B, C, D, and E. My simplices are going to be, all the vertices, all of the edges that I've drawn, A, C, A, D, C, D, B, E, and then the single triangular face that I've shaded in. Okay, and so some facets would be A, B, C, but also, for instance, D, E, this edge, and also AD, since I haven't shaded in the triangle ACD. And the dimension of the triangular face is 2. The dimension of any edge will be 1. And so you can see that the dimension of my simplicial complex is 2. So there are any questions about the setup here? I'll probably, anytime I ask for questions, I'll probably pause for longer than you think is necessary, but this is just a habit from teaching and talking to a lot of blank screens, having to wait for a lot longer. So bear with me in the awkward silences. All right, but I'll move on. So how do we go from these simplicial complexes to hypergraphs and back again? You could probably guess by the way that I defined it or the way that I drew it, that if you have a hypergraph H, and for all of my pictures, I'll just draw R equals 3, since that's sort of the easiest non-trivial example to draw. I can just take the down closure of any edge of size R that I have in my hypergraph, and that is what I will put in my simplicial complex. So I can sort of take my R uniform hypergraph, or really any hypergraph, but we're only going to be thinking about R graphs, and have it correspond to this simplicial complex. And then I can talk about homeomorphisms between these simplicial complexes. So for instance, this simplicial complex, if I just look at this single hyper edge or the single facet that I've drawn, this is homeomorphic to, the disk, this one. In general, when I'm talking about homeomorphisms, we're not going to be worrying about any, technical aspects of homeomorphisms. You can really just think of triangulations of spaces when I'm talking about homeomorphisms. We're not going to be dealing with anything too weird. So this is sort of the picture that you can have in your mind is, a triangular face is homeomorphic to the disk, and a triangulation of the sphere is homeomorphic to the sphere. Right? So now I can tell you what the actual problem that I'm trying to solve is. Was there a question?
Yes, yeah, sorry,
Yes.
I couldn't unmute myself earlier.
Oh, yeah, it's fine.
What does maximal mean for a facet? I was surprised to see a couple of them. I would have expected just a shaded triangle in your previous example, but then you had extra edges.
What do you, so I have multiple facets. So I'm defining a facet as a maximal face, which means a face that's not included in any larger face.
Okay. Yeah. Sorry. Thank you. It's by inclusion.
Right. Yeah, of course.
Right.
Yeah. So that's important. So in the actual problem that we'll be considering, we'll have all of our facets will be of the same dimensions. So we won't actually need to worry about facets of different dimensions. But I just had this to illustrate that, you know, this is a facet and this is a facet, but this facet is the one that determines the dimension of your simplicial complex. Yeah, that's a good question. Thank you.
Great. Thank you. Sorry.
No, fine. Any other questions? Yeah, I want to make sure we sort of understand the structures we're dealing with before I move on to more complicated things. Okay, great. Yeah, feel free to ask any, if you want me to go back to anything. Don't feel like it's too late to ask any questions. Okay, so now I can tell you I've given you the topological point of view that's going to be these simplicial complexes. Now, what is the question that we're actually asking? And this question was first posed by Nati Linial around, I think, 2008 or so, and it was part of his, high dimensional combinatorics program, where he was really saying that the sort of next frontier in combinatorics is to take this topological point of view for all of these classical combinatorial problems. And as a side note, a lot has been done in this area on like random simplicial complexes and adding randomness to these topological structures. But one of the questions that he posed today, it's not related to that, is this one, which is the topological version of Teran's problem. So given a K complex S, and what I mean here is a, K dimensional simplicial complex. How many facets? And again, I assume these are all K dimensional. Right. So this is, in keeping with our correspondence between uniform hypergraphs and our simplicial complexes. All our edges in our hypergraphs have the same size, so all of our facets should have the same dimension here. So how many facets can an n-vertex K complex have while containing no homeomorph of S? So this is the Teran problem that I am considering. And what was already known when Nati first posed this question? Well, it was already known that you can find a specific lambda of S, which is an exponent associated to any given K complex S, such that this many facets, some constant times n to the K plus 1 minus lambda of S facets, is enough to find a homeomorph of S. So let me say why n to the K plus 1. So why n to the K plus 1, right? It's because the maximum number of K facets possible is n choose K plus 1, right? Which is, n to the K plus 1. So we're sort of comparing it to how close do you need to get to the maximum number of facets you could have before you start seeing homeomorphic copies of S. And this result, we sort of cited in our paper as folklore, but you can also read it off of some of Erdős's results on these, what I mentioned earlier, degenerate Teran problems. So this was already shown. And the main question that we're considering now is, can we find some so-called universal exponent? Can we find some lambda K that provides a lower bound to all of our lambda of S's that only depends on the dimension K? So this was the main question that we were considering. And let me tell you some of the results that were already known in regards to answering this specific question. So the first was by Mader in 1967, and he showed the exact exponent for lambda 1, right? Lambda 1, this is for just, sort of normal graphs. So this is guaranteeing homeomorphs of just normal graphs. And homeomorphs correspond to just subdivisions of, graphs. And so Mader didn't phrase his results in terms of topological Turán. He said, a linear number, pick your favorite graph. A linear number of edges is enough to guarantee a subdivision of that graph. And in fact, that's tight up to constants. Right, so a linear number of edges is enough to guarantee a subdivision of H. Okay. And then the first sort of result in terms of higher dimensions was this Brown, Erdős, and Schoch result that determined the exponent specifically for the two-sphere. And they showed that lambda of S is equal to 1/2. And let me say a little bit about this, since this is one of the points where I can mention relationships to additive combinatorics, because one of the bounds that Brown, Erdős, and Schoch proved actually relied on some results within additive combinatorics. So let's look at the lower bound. So what does proving the lower bound for this result mean? It means we want to find some 3 uniform hypergraph, which is, equivalently a 2-dimensional complex on some constant times n to the 5/2 edges with no triangulation of the two-sphere. Right, so we want to show that we can find some hypergraph that doesn't contain any homeomorph of the two-sphere, and really we're just looking at, we can think about that as triangulations of the two-sphere. So the lower bound involves constructing a very particular hypergraph. And how are we going to construct that hypergraph? So the construction, we're going to use a result from Singer about perfect difference sets. So Singer said, if we take M to be p squared plus p plus 1 for p prime, then there exists, I'll call it D, contained in Z mod M, such that D is a perfect difference set. And what that means is that for any, let's say, X in Z mod M, there exists a unique pair, D1 and D2 in D, such that X is equal to D1 minus D2. Right, so every element in Z mod M can be written as a unique difference between 2 elements in D. Let me sort of separate these things. And you can tell sort of by the definition of M as being p squared plus p plus 1 that the proof of this has to do with sort of, finite projective planes and the geometry of those. So let me not go into the proof of this theorem, but how did this relate to our construction of our hypergraph that doesn't have any triangulations? Oh, that was supposed to be a straight line. Here we go. So our hypergraph, we end up taking 3 copies of Z mod M, and the vertices correspond to, you know, these residues. So we take 3 copies of Z mod M. And we say that, you know, X, Y, Z is an edge in our hypergraph if and only if X plus Y plus Z is in this perfect difference set. So that gives some, you know, that gives some additive structure to this hypergraph that we have constructed. And what you can show is that now you can just use properties of triangulations of the two-sphere. So for instance, we know that in any triangulation of the two-sphere, if we were to take a look at any vertex, for instance, in the graph, if we looked at sort of the graph induced on its neighbors, right? Yeah, so if we looked at what happens here and we just looked at the graphs on its neighbors, then in order for this to be a triangulation, that graph has to be in the form of a cycle. So you can sort of think about, if you think about, yeah, like a tetrahedron or something, that sort of is the picture that you can have in your head. Sort of generalizing a tetrahedron to just, you know, you have a vertex and there's a cycle coming out of it. And you can show that this is going to be true for, that this has to hold for any vertex in the graph. You take out the vertex and what's left has to be a cycle. But if you look at this graph that I've constructed, if you pick out any vertex and what's left is a cycle, that tells you something, you know, something about that cycle and whether or not that cycle can exist based on this condition that you've imposed about the additive structure of it. And, you know, I won't go too much into the rest of the argument, but you basically use properties of that cycle and some other properties of degrees and triangulations to essentially say that there's no way that any triangulation could exist in this particular hypergraph. Yeah, Sean.
You absolutely need a perfect difference set, or would any sufficiently large CDOM set work? As in, go ahead.
Yeah, I actually I'm not sure about that. I don't I haven't thought about whether or not you can sort of relax this condition. But yeah, that would be interesting to think about. It seems to me that this requirement, the fact that we are using that sort of any arbitrary vertex, you know, has to have this relationship to all of the other vertices in the cycle, means that all of the other vertices have to sort of satisfy this perfect difference condition. But yeah, I'm not sure. Maybe if you take it to be large enough, then it might work. I would have to think about that. That's a good question. Yeah.
Thank you.
Yeah. Any other questions before I move on from this proof?
Can I ask one?
Yeah, Charlie.
So you could order the 3 sets in some lex order or colex or something, and then take the, you know, a greedy algorithm that just takes whatever 3 sets it can without completing any 2 spheres. How does that, you know, what kind of bound would that approach get? Or
sorry, can you, so you want to take your 3, so you're trying to construct a hypergraph with no triangulations, and you're saying
with with no triangulations of 2 spheres.
Mm-hmm.
And the thinking was just, what does the simplest, you know, or greedy algorithm give us? Because this algorithm is more clever, the 3 Z-mod MZs.
Yeah, so you're saying essentially just sort of throw in edges until we would potentially create a triangulation and then, you know, sort of skip the next edge.
Yeah.
Yeah, I don't know exactly what bound that would give, but I don't think it would be nearly as good as this one. I yeah, I think you would end up with less than n to the 5 house. But I haven't worked out precisely what the details would be. Yeah, but I'll say a little bit about, maybe I'll address this later, and when we talk about sort of generalizing results and is it possible, well, I'll just say a little bit about it now. You know, the results that I'm going to talk about are mainly combinatorial in nature, because when we go to higher dimensions, there is, you know, a barrier between what you can say about, you know, two-dimensional objects and three uniform hypergraphs versus when you go on to higher dimensional complexes and you know, higher uniformities, right? There's just much less that we understand. And so sort of the a greedy sort of algorithm could always work in those higher dimensions, but I don't think it's going to get you an optimal result. And we'll see that even with the proof that I talk about today, we are being a little bit more clever than doing a greedy algorithm, and our bounds are still far, far, far from optimal. So I anticipate that the greedy algorithm wouldn't do very well here. Other questions? Okay. So then let's move on from the historical results to what's been done more recently, since Nati Linial posed this question of what is this universal exponent. So at the beginning of last year, actually about a year ago, Peter Kivash, my two co-authors, Jason Long and Bhargav Narayanan, as well as Alex Scott, showed the first lower bound for the exponent in 2 dimensions. So lambda 2 is at least a fifth. And last fall, around the same time as the result I'll be talking about, these 4 authors, Kupovsky, Polyansky, Toman, and Zakharov, showed that the exponent is exactly 1/2, not only if we have the 2-sphere, but in fact, if we have any closed orientable surface. And so it's natural to conjecture that the correct answer is actually lambda 2 is equal to 1/2. But we still don't know. But you could also ask what happens for higher dimensions, as I just said, you know, 3 complexes or general K complexes. And so that's what I'll be talking about today. In fact, we showed that lambda K does exist for all dimensions, and that we can give it a lower bound of K to the negative 2K squared. But you'll notice that this is far from tight, as I hinted at. For instance, it gives you lambda 2 is bigger than 2 to the negative 8th. And we already showed that it's bigger than 1/5. We conjecture that it's actually equal to 1/2. But the advantage of this proof is that it's purely combinatorial, whereas the previous results had very dimension-specific arguments. So for instance, when I was talking about the sphere, right, it relied on this very specific construction using perfect difference sets. When we're talking about these 2 results, the first one for the lower bound of lambda 2, you know, also relied on sort of specific geometric properties of the homeomorph that we were looking at, or that they were looking at. And of course, this result for closed orientable surfaces used what we know about closed orientable surfaces, mainly the classification of surfaces. And those are things that we just we don't know in higher dimensions. Oh, I don't know in higher dimensions. So if you know things about, you know, triangulations in higher dimensions, I would be very happy to hear about them after the talk. So that was sort of the main draw of the proof of this theorem, was to eventually let go of the topology and sort of the geometry underlying the arguments and just focus on combinatorial concepts. And we're using 2 main tools. One is this notion of a trace-bounded hypergraph that I'll introduce, and the other is this well-known technique called dependent random choice, which I'll go over. So before I go on, so I'm going to spend the rest of the time talking about the ideas that go into the proof and these specific tools. But before I do, are there any questions?
So I'm still trying to understand what universal means. Is lambda K simply the minimum of lambda S overall?
Yeah.
K complexes S?
Yes. Yeah, exactly. Yeah. And so there's a question of like, is this lambda k actually tight for all of our simplicial complexes S, right? Are lambda S is going to be the same for all simplicial complexes? There's this idea of, you know, in the k equals 1 and 2 cases, you know, for subdivisions, sort of the idea is once you start to see cycles, then you sort of start to see everything in your graph. And in the k equals 2 case, it's like when you start to see triangulations of spheres, then that pretty much guarantees you every surface. We don't know that, but that's the conjecture. And so a good question to ask is the k-sphere the correct answer for every dimension? In fact, or is there this gap in some dimension between lambda k and some lambda of S for some S? And we don't know that. We don't know the answer to that. Yeah. Other questions? Okay. So then let me go on to talk about the techniques that we used in our proof. So let me start with the notion of trace-bounded hypergraphs. So I'll define the trace of a graph on a subset of vertices. You can think about it as sort of the projection of the hypergraph or the edges onto that subset. I'm just taking every edge in my graph and I'm intersecting it with my chosen subset of vertices. And I'll use this notation if I'll mainly be dealing with R-partite graphs. So for an R-partite, R-uniform graph, R-partite meaning, you know, I have an edge of size R, one vertex is in each part. I'll denote my set of vertices as X1 through XR, and I'll say that the trace sub I, or the ith trace, is the trace on the first I parts of my graph. And then I can define this new term of D trace bounded if I have this degree condition, if the degrees in my ith trace are bounded for all vertices in my ith part. So this is a little bit of a weird concept to think about, so I think I should just draw an example and hopefully it'll be clear from there. And again, let me draw R equals 3, since that's the nicest non-trivial example. And I'll label my parts a little bit backwards from what you might want me to label them, and you'll see why. So let's say that this is my G. And what does it mean for G to be D trace bounded? Well, I want to look at each I. So let's first start with I equals 3. Then I want to look at the ith trace. So what is the third trace of G? Well, that's just the projection of the edges onto parts X1 through X3. Well, that's going to be all of G. Right, the set of edges in G, because I'm just restricting all of my edges to all 3 parts. And my condition is that the degrees in the ith part are bounded. So the degrees in X3 are bounded for all V in X3. So what that tells me is that if I have V here, then I have edges coming out of here. I have at most D edges coming out from any vertex in X3. So just as a general, in the general graph, all of my degrees in X3 are bounded degrees. Okay. So then let's take a look at what happens when I equals 2. Now, my second trace is going to be restricting all of the edges to here. Right. So my second trace is just a normal old graph. So this is a 2 graph, or just a normal graph. Then my condition is that all of my vertices in X2 have bounded degree in this graph. So that means for any, let's say U in X2, all of my degrees from U to X1 are bounded. But I'm allowed to have as many edges as I want in terms of D going back to X3. So in the general graph, the degrees in X2 might not be bounded by some function of D. And then if I look at I equals 1, right, then my trace is just going to be x1. And so I don't have any conditions here, right? I just have, this set of vertices, and my trace boundedness doesn't impose anything about x1. So in particular, the degrees in my x1 could be unbounded in terms of D. So the reason that I drew it like this is I like to think that the forward or rightward degrees are bounded by D, right? So in that direction. And then the backward degrees can be unbounded, can be arbitrarily large in terms of D. Right. So are there any questions about the notion of D trace boundedness? Right. Now at this point, I can actually state the main combinatorial result that we showed, which was just a result about D trace bounded hypergraphs. So in fact, the bulk of our work was to prove this theorem, which is that we can find some alpha RD, some constant just in terms of the D for trace boundedness and the R for the R partite R graph. And I have this sort of Teran result for these particular graphs. I can find this alpha such that any R graph with at least this many edges, so n to the R, then minus this exponent of alpha RD, contains a copy of H. So now I'm ignoring the topology altogether. Now this is just a result about the Teran problem for hypergraphs. If I have this many edges, then I can find a copy of my favorite, an isomorphic copy of my favorite D trace bounded hypergraph. And if you're familiar with any of the background for this problem, you might notice this gives a universal lower bound for what are called the Teran exponents for degenerate trace bounded hypergraphs. And this generalizes a previous result by Conlon, Fox, and Sudakov. So they proved something very similar, but under a more strict assumption. They said that, x1 through xr minus 1, let's say for our parts, have bounded degrees. Right, so not just this like forward degrees are bounded, but overall in all but one of the parts, the degrees are bounded. So their result was a little bit had stronger assumptions. So from here we can actually prove our theorem 1, which was about finding copies of homeomorphs, right? So how do I get from homeomorphs to just D trace bounded graphs? So let's suppose that I have my simplicial complex, and let's say that I have a bunch of facets that look like this. And again, just drawing for the case R equals 3. Let's say that I have these facets in my simplicial complex, and I want to find a homeomorph of it. I'm going to construct a very particular homeomorph of my S, which I'll do by subdividing all of the faces contained in my facet, other than the vertex, of course. So I'm going to add a vertex to subdivide the facet itself. And then I will also add 3 vertices to subdivide each of the edges. And then I'll take each of these 6 new facets to be facets in my simplicial complex. So now I have 6 facets. And this is going to be my homeomorph that I find in my simplicial complex. And what you might notice from the way that I colored these vertices is that this is actually going to correspond when we go from our simplicial complex to the hypergraph to a D trace bounded 3-partite 3 graph. So how do I do that? Let me draw the parts in the corresponding colors. So I want to show that this is actually D trace bounded. So let's look at the pink vertex first. What's its degree going to be in this homeomorph? Well, it's only ever going to be adjacent to these 6 facets here, right? It's only ever going to be included in exactly these 6 facets that I created from subdividing this original facet. So each of my pink vertices are going to have degree at most 6, exactly 6. This is a 3-partite graph. Okay, so that gives me the vertices in my X3 are bounded. Now, if we look at my X2, right? In general, these degrees might not be bounded in terms of, some constant d, right? For instance, if in my original simplicial complex, I had like a bunch of facets sort of coming off of this particular edge. If I had a bunch of facets that were containing this particular edge. So the green vertex might be adjacent to some really large number of vertices. But in terms of the black vertices that it's adjacent to, it's subdividing this particular edge. So it will only be adjacent to these 2 black vertices. So in fact, its degree to X1, the set of original black vertices, is bounded by 2. So this is less than 2. And then I don't, the D trace boundedness, I don't need to assume anything about the black vertices. And of course, I shouldn't because, again, the original vertices might be involved in a lot of different facets in my simplicial complex. So what can I say from here? I can say that if I can embed H, then I get a homeomorphized simplicial complex. So let me write that down here. Here. So to find a homeomorph of S, it's enough to find a copy of H, right? Where this is my, this is the H that I drew. So we've reduced our original topological theorem to just finding copies of just hypergraphs in a denser hypergraph. So are there any questions about how we got from theorem 1 or how we got theorem 1 from theorem 2? And I should say, in general, you can do this for higher uniform or higher dimensions. In general, you will have your D for the D trace boundedness will be something like k plus 1 factorial when you're looking for k-dimensional simplicial complexes. Based on, doing this sort of analogous subdivision for each of your facets. Is there any questions before I go on? So now for the rest of the time, I'm just going to talk about proving this theorem too. So now we are leaving the topological world behind completely. We are no longer going to be talking about simplicial complexes. We are only talking about the combinatorial aspect, and that is for finding the copies of trace-bounded hypergraphs in denser hypergraphs. And to prove this theorem too, I'm going to use the idea of dependent random choice. So let me say a bit about what dependent random choice is. So my notation will be this. Again, I have my G, and I can assume it's an R-partite hypergraph, just because I can use sort of an averaging or an expectation argument to pass to an R-partite subgraph with still enough edges in it. And I want to find a copy of my H, which is my D trace bounded R-partite R graph, and I'll say that it's on parts Y1 through YR. And in order to find a copy of H in my G, I want to construct some sort of embedding from H into G. So let's just say that I have 2 parts for now. Let's say I have X2 and X1, and maybe there are other parts, but I'm only going to look at the first 2. Actually, let me make these Y2 and Y1. And H and I have my x2 and x1 in G. And let's say that I have already found some embedding of y1 into x1. So I have my y1 here. Let's say phi of y1. Then what do I need to do in order to find in order to embed the next part, y2 into x2? Let's say I have some vertex v here. What are my candidates for the image of v in x2? Well, what I would want to do is I would want to look at all of the neighbors of v in y1. So this is the neighbors of v. And I would want to see where phi sent those neighbors. So maybe it sent them there. And then a candidate for v, for phi of v, would be all of the common neighbors of phi of the neighborhood of v. So my candidates for phi of v are the common neighbors of phi of n of v, right? Because I need phi of v to be adjacent to all of its neighbors. So ideally, I'd like to just, sort of proceed with this embedding greedily. I'd like to be able to look at all the ones that have not been picked yet and just sort of randomly choose one of these to be phi of v. But what's an obstacle we could run into, right? An issue that we could have is, what if I've already embedded some vertices before I reach v? And maybe by the time I reach v, all of those vertices have been embedded into the common neighborhood of phi of n of v, the neighborhood. Then I'm out of luck. Then I don't have any options for sending v. I noticed there might be something in the chat, but oh, Charlie, we're not gonna be talking about that. But thanks for the comment. So an issue, so an obstacle to a greedy embedding in this way. So by looking at sort of the common neighbors of my embedded neighborhoods is if the common neighbors if the size of the common neighborhood of phi of n of v is too small, right? If it's possible for me to sort of run out of options by the time I reach v. So what dependent random choice says, so I'll say dependent random choice says there exists a good subset of x1 such that sending y1 to this subset avoids the above obstacle. Right. So in more precise terms, dependent random choice says we can find a place to send phi, to send y1. So we can find a candidate for this pink set such that every subset of a particular size, so every subset that could potentially be one of these phi of n of v's, every subset has a large common neighborhood. And so if we can guarantee that every subset has a large common neighborhood, then we avoid this obstacle. And that's what dependent random choice essentially tells us. And why is it called dependent random choice? The way that we find this good subset is by taking a random subset of x2 and looking at its neighbors. So rather than taking a random subset of X1, we sort of look at a random neighborhood in X1. And it turns out that that random neighborhood has this property that every subset has a large common neighborhood. Okay, so dependent random choice is we're going to use a variant of it on the next slide in this proof, but you know, I want to mention that this technique has a lot of applications, not just within extremal and probabilistic combinatorics, but also you know, a lot in Ramsey theory, a lot in additive combinatorics. It's crucial in the proof of the Balog-Semerany-Gowers theorem. So it's not just something that is only used for these sort of Teran embedding type problems. It has a lot of applications elsewhere. So I'm running a little bit out of time. So let me just sort of sketch how we use dependent random choice, right? What were the obstacles that we ran into? Because we're no longer, for our problem, we're not embedding just two parts here. We have our parts sitting out here. So how do we sort of extend this embedding to find our trace-bounded hypergraph? Right, our potential obstacles now are not just small common neighborhoods. Our obstacles are if we don't have enough extension possibilities. So if I look at the link of any vertex, and I define the link as, you can think about it as sort of the projection sort of onto a neighborhood of a vertex, of the edges onto a neighborhood. It's just looking at all of the edges that involve a vertex V and deleting V from each of those edges. So let's say that I have a vertex V and I'm looking at its link. And let's say it looks like this. Maybe it's this 4 cycle. And let's say that this is an H, and I've already embedded this into G. I've found a way to find the specific set of edges in my G. Now, how do I extend it to include V? It's not just that I want V in the common neighborhood of these two vertices. I actually want V to be able to extend, to be able to extend each of these 4 edges, right? So I'm looking at not just subsets of vertices, but actually subgraphs and all of the possible subgraphs that could come up. And I want to say that, you know, before I wanted to say every subset has a large common neighborhood. Now I want to say every subgraph like this has is in a lot of links. So I want every subgraph is in a lot of links, so that I have a lot of ways to extend in G. So that I have a lot of ways to extend this subgraph to a vertex in G. But if I just say like every subgraph, there are a lot of possible subgraphs that could come up in these 2 parts. So this seems like infeasible to demand something of every subgraph. But it turns out that we don't need to look at every possible subgraph that could come up in these 2 parts. We now use our D-trace bounded hypothesis, right? Because what are the possible subgraphs that could come up as the link of a vertex? They're only the subgraphs that have at most D edges, because I've demanded that my forward degrees are bounded by D. So there are only at most D edges in this subgraph that I would have to extend. And so this comes from the D trace boundedness. So if I just look at the collection of graphs that have at most D edges, then sort of the bad subgraphs would be the ones that cannot extend to very many vertices. And essentially what I want to do is sort of a dependent random choice type argument that says, I don't run into this obstacle. And I can find a subset where I don't have any bad copies of these subgraphs. And so the sort of main lemma was that, you know, we can guarantee this, that this sort of, this subset exists, that if we have a T-part type T graph, with a lot of edges and few bad copies of these subgraphs, we can find a T-1 partite T-1 graph with a lot of edges and few bad copies of these subgraphs. So we can essentially iterate, and I'm being very vague here, I'm not including any of the sort of numerics of it all. We can sort of iterate until we find a place to embed our graph that avoids these sort of bad copies of subgraphs. So that is sort of the vague idea of what we did in this proof and how we were able to embed our partite R graph, you know, sort of piece by piece. Okay, so that was the main idea of the proof and how we sort of use dependent random choice-esque result that relied sort of on subgraphs rather than neighborhoods. So that sort of ends the proof as a whole. So let me just say a little bit about open problems, which I've already mentioned earlier. It would be interesting, of course, to find the optimal values for these lambda k's. In particular, is lambda 2 equal to 1/2? We still don't know. I really think that lambda of sk, the k-dimensional sphere, could give us an idea of what the optimal value for lambda k is, but that sort of involves understanding more about triangulations of the k-spheres, which I don't understand at all. So if someone understands something about triangulations of k-spheres and wants to tell me about it, I'd be very happy to hear that. And then the last open question is just, you know, forgetting about the topology and just looking at the second theorem about trace-bounded hypergraphs. Are there optimal values for these so-called Teran exponents? Can we just look at the combinatorial version of the problem? So these are sort of the main open questions left over at the end of our paper, but I will finish here and say thank you.